Okay, section 7.5, where we're going to be doing addition, subtraction, multiplication, division with radical expressions. When you have radical expressions, as long as they have like roots, in other words, the index is the same. So in this case, we have a square root, this is a square root, this is a cube root, this is a cube root. When you have the same like roots, then you can multiply the two radical expressions, and you can do it by putting them all under the same radical sign. So, the one on the left, 10x squared y times 40xy cubed, we can combine the number terms and can combine the x's and y's and put them all under the same radical, and we're going to get 40 times x cubed times y to the fourth. Now we're talking about a square root here, so we want to find, again, remember we're trying to simplify these. Okay, there's my dog going crazy. So we are looking for perfect squares underneath the radical, and we find a couple. 20, we have 2 squared times 10 squared, which is 20 squared. We have x squared, and with a little x left over, to have a total of x cubed, and then we have y squared, quantity squared. So we can now pull out a 2 and a 10 and an x and a y squared, and we're going to be left behind with just that leftover x from that x cubed term. Now we want to ask ourselves, do we need to worry about absolute value here? Because you have, as it turns out, an odd value of the x that came out. But if you look at your original function up here, if you look at your original function, you have both of these have to be positive. These are considered principal roots. And because you have an odd one here, then you would have to consider this x value has to be positive. So we know that x has to be positive, therefore we don't have to worry about the absolute value. So the answer is no. Okay, next one. Cube root of 72a to the fourth, cube root of 81a squared. Because they're both the same index, we can go ahead and combine them under the same radical. With the index being 3, so we're going to combine the numbers. That's going to be 9 times 8, and I'm factoring them because I'm looking for perfect squares. 9 times 8, and then we have a to the fourth and a squared. I can combine the a to the fourth and a squared, and I can combine the numbers, but I'll probably keep them factored. So I have a 9 cubed times a 2 cubed, and then I have an a squared, and that is quantity cubed. So that's a to the sixth, right? A to the sixth, the same as a squared raised to the third power. So we have each term raised to a third power. Now we can pull these values outside of the radical. We'll get a 9 outside, a 2, and an a squared. We'll combine those terms to get 18a squared. Again, what about absolute value? Don't have to worry about it because we're talking about an odd index. We only have to worry about absolute value when we have an even index. Okay, now if we're multiplying radical expressions, we can use the distributive property. So we're going to have to take 5 radical 2 times 3 radical 6 and negative 4. And we just kind of carefully have to write it out. Now I know this is going fast, so feel free to pause your video in order to catch up with your notes. But we're taking 5 radical 2 and multiplying by each of the terms. Now that we've multiplied it out, we can combine the number terms and combine the radical terms as long as the radical terms have the same index. In this case, they do. So 5 radical 2 times 3 radical 6 is the same as 15 radical 12, and then we're going to get 20 radical 2 for the other term. That 15 radical 12 looks like it can be simplified because we have a perfect square inside with our 4 times 3. So we can pull out the 2, and we'll get 15 times 2 with the 3 left over under the radical, minus 20 radical 2, and that will give us 30 radical 3 minus 20 radical 2. Now, you cannot combine these two terms any further. Because the values under the radical are different. So that would be like an A and that's like a B. I mean, they're two different values. So you cannot say 30 minus 20. You can't say 10 like radical 1 or something weird like that. You have to keep these separate because they are different. Okay, next one. We're going to be dealing with radical 2 plus radical 3. This is treated like a binomial where you're going to FOIL it out. So you would write out both terms, probably the easiest way to do it. Square root of 2 plus square root of 3 times square root of 2 plus square root of 3, and then FOIL first, outside, inside, last, and then combine or multiply terms under the radicals and combine. So I'll write them out one by one, And now I'm going to combine terms that are under the same index, so we can go ahead and put them under the same radical. So I'm going to get 2, square root of 2 times square root of 2 is just 2. And then I get radical 6 plus radical 6, and then the square root of 3 times square root of 3 is just 3. I can combine further to get 5 plus 2 times the radical 6, because radical 6 plus radical 6 is just 2 radical 6. Okay, moving on. Radicals may not be left in the denominator of a fraction, so we will be rationalizing the denominator. We did this before with square roots, and now we're going to do it with other types of roots, and it's going to get a little more difficult. But it's the same concept. So, for example, square root of 40 over square root of 81 is, well, we'd simplify it if we can, 2 squared times 10 over 9 squared. So that isn't too hard to do. We just go pull out the 2, we get 2 radical 10 over 9. That is a considered rationalized because there is no irrational number or square root in the denominator. So we're good with that one. Okay. 4 over square root of 2. Remember, we did this before. In order to get the radical out of the denominator, we're going to multiply the bottom by the square root of 2, and then we'll multiply by the top by the square root of 2. What we're doing essentially is multiplying by the number 1. So I'll put that whole thing, and it looks like a giant 1. By multiplying something over itself, you're multiplying by 1, and that's how we're going to deal with rationalizing radicals in fractions. So I multiply these out, square root of 2 times square root of 2, and the denominator is going to give me 2. I get 4 radical 2 in the numerator, and so that will simplify to become 2 radical 2, and that would be my final answer. Okay, taking a look at, now we've got some variable terms, and we want square roots, so let's pull out what perfect squares we do have. So we'd say that we have, first of all, I'm going to separate them. So I have a square root of x to the 5th on the top, a square root of y cubed on the bottom. And that, if we can now multiply top and bottom by the square root of y, that will give us a perfect square in the denominator. It'll be the square root of y to the 4th. And then we can simplify that. So we're going to end up with square root of x to the 5th times y up above, and the square root of y to the 4th down below. You see, I had an odd radical, and I can't simplify that totally. So by multiplying by one more square root down here, by multiplying by one more square root, this term becomes y to the 4th, and now I can take the square root of that, and I'm going to get y squared. I need to know where I'm going so I can figure out how to get there. And the goal to get there is to get rid of any radicals in the denominator. Okay, so let's think ahead now. Square root of 4y over the square root of 5x cubed. What am I going to multiply to get this variable and the square root out of the denominator? I need to have a perfect square down below. So what could I multiply this bottom term by to make it into a perfect square? Sorry, I hadn't finished the last one, so let me go ahead now. Square root of 4y over square root of 5x cubed. I first separate the two, and now I need to figure out what I'm going to multiply by. Now, if I multiply top and bottom by the square root of 5x, then I'm going to have square root of 25x to the 4th down below, which is a perfect square that I could simplify. So, up above I'm left with square root of 20xy. Down below I have square root of 25x to the 4th. That I can now simplify to 5x squared, and then I will have a rational denominator. I don't think I can simplify that any further in terms of canceling, so that would be my final solution. Okay, radicals may not be left in the denominator of a fraction, so we're going to keep doing what we did before, except this is a little different. We got a cube root of 9. So what can we multiply by the cube root of 9, which is the cube root of 3 squared, in order to get this denominator to become a perfect square? So what we want to do is multiply by, well, keep in mind that's the square root of 3 squared. So we want to multiply by the cube root of radical 3. By multiplying the bottom by the cube root of radical 3, it's going to become the cube root of radical 27, which is a perfect cube. If we multiply the bottom, then we also have to multiply the top. Okay, so let's go ahead and simplify. We're going to get 8 times the cube root of 3 up above, And then down below, we're going to get the cube root of, now, 27, which is 3 cubed. So then we can pull the 3 out, and we're left with 8 cubed radical 3 over 3. Okay, next problem. 6 over the 5th root of 8a squared. Okay, we need to turn the denominator underneath the radical into a perfect fifth, okay, something raised to the 5th power. So what will we multiply the bottom by to get it to a perfect fifth? 8 looks like it's 2 cubed, okay? 8 is 2 cubed. We need to have that be 2 to the 5th. So we're going to have to multiply that by 2 squared. A squared, we need to multiply that by a cubed in order to get it to the 5th. So we're going to take the whole denominator and multiply it by the 5th root, don't forget that index, the 5th root of a cubed times 4, or 2 squared. If I multiply the denominator, I also have to multiply the numerator, and I get the same fraction. Okay, so now I'm going to multiply it out, both sides, top and bottom. I'll get 6 times the 5th root of 4a cubed over the 5th root of 32a to the 5th, which will now simplify to just 6 times the 5th root of 4a cubed over 2a. And that can further simplify because we have fractions that will reduce, and we'll get 3 times the 5th root of 4a cubed over a. Okay. If you have a denominator which is a binomial, it's not really a binomial because there's no variable, but it looks like it because it has both a number or an integer and a radical, we can eliminate the radicals in the denominator by multiplying by a conjugate pair, like we did when we were dealing with binomials. So if we multiply the bottom by 3 minus radical 3, then we can eliminate the radical in the denominator. And if we multiply the bottom by 3 minus radical 3, then we also have to multiply the top by 3 minus radical 3. So here we go. Let's multiply it out. 4 times 3 minus radical 3 is going to be 4 times 3 minus 4 radical 3. 3 times 3 plus 3 radical 3 minus 3 radical 3. And we have a minus 3 radical 3 times 3 radical 3. And okay, so now you can see this simplify because the 3 radical 3's are going to drop off. We're going to get 9. Okay, I'm simplifying the top part. We're going to get 9 minus 3, which further simplifies to 12 minus 4 radical 3 over 6. And since there's a factor of 2 on top and bottom, we can eliminate that and get 6 minus 2 radical 3 over 3. Okay, and last one. We want to get rid of the radicals in the denominator. So what do we multiply top and bottom by to make those go away? If we have two numbers being subtracted, then we're going to multiply by the conjugate pair, which is going to be square root of 5 plus the square root of 2. If we do that in the denominator, we have to do it in the numerator as well, because we're multiplying this expression by 1. That's always okay, to multiply by 1. So square root of 5 plus square root of 2 in the numerator. Now I'm just going to multiply it all out. Square root of 5 times square root of 5 plus square root of 5 times square root of 2 all over square root of 5 times square root of 5 minus plus 5 radical 2 minus radical 5 radical 2, which will go away, minus radical 2 times radical 2. So we can simplify. We're going to get 5 plus a square root of 10 up above and 5 minus 2 below. That will further simplify to 5 plus radical 10 over 3. And that concludes our lesson for today.